Good afternoon for European viewers, good morning for US attendees, good evening for Asian and Australian attendees, and good luck for others. I'm Gérard Bailly, Senior Researcher at GIPSA Grenoble, France. I'm quite honored to take part of this Furhat webinar. In this quick presentation, I will pinpoint some details that may strongly impact the training of social robots, hoping to trigger interesting discussions. Social robots are now endowed with incredible sensory motor and cognitive skills, enabling challenging tasks in the field of industry, education, or healthcare. As an example, our iCube robot Nina was trained to conduct neuropsychological interviews with elderly people using multimodal data collected during real memory tests. Let's have a look. It's in French, sorry.
On va apprendre ces mots ensemble. On va les apprendre petit à petit, 4 par 4. Donc il faut bien vous concentrer pour bien tenir les mots que je vous montre. D'accord. Alors voici les 4 premiers mots. Est-ce que vous pouvez me dire le nom du poisson?
Hareng.
Oui. Le nom du vêtement?
Gilet.
Oui. Le nom du jeu?
Domino.
Et le nom de la fleur?
Qui est la fleur?
La fleur, traduis-moi.
Jonquille.
D'accord.
Endowed with such interactive behaviors generated by end-to-end HRR models, social robots may achieve task performance that competes with their human tutors. But they are still implementation and methodological details that are often overlooked. I brought 5 of them today. Design, so generating readable behaviors. Multimodal orchestration, designing intricate sensory motor loops. Teaching framework, learning affordable and acceptable skills. First contact, mastering expectation, in particular when there is this first contact with the person and the robot, and evaluation issues, enabling diagnostic. Finally, I will suggest an ultimate challenge for which such issues are essential for social robots, replacing human congeners for probing their sensory motor, cognitive, and emotional abilities. So using robots as proxies to probe human cognition. Okay, let's start this tour with eye design. Despite the critical role of gaze in HRI, social robots have been equipped with an incredible diversity of eye morphology, if any. You have still robots as cosmonauts without eyes. Interestingly, Elon Musk masked the face of a real human to introduce his Tesla humanoid. Clearly, bipedal walk is not the main trait that differentiates humans from birds and apes. By the way, does the proverb, no matter what the bottle, as long as you get drunk, holds for eyes and gaze? Is the estimation of his eyes' direction independent on their morphology? Actually, the human eye morphology is especially designed for cooperation. Eye direction is an essential component of our theory of mind. Thanks to the very details of our eye morphology, large width to 8 ratio, large sclera to outline ratio, large sclera to iris contrast, we share our emotions, intentions, points of interest. We select our addresses. We share this for free. I recall here that Tamming the Mona Lisa effect originally motivated the development of Furhat. Note that the comparison between Furhat and a 2D display was truncated to 53 degrees of angle. I discuss this in the following. The human eye outline is not fixed. 15 years ago, prehistorical research, well before science was dominated by machine learning, we showed that the eye outline varied with eye direction, so that to maximize foveal exposure, for example, the eye outline opening when looking laterally, either left ear or right, and the raising, in fact, of the upper lip, of the upper eyelids when looking up, as well as eyeball protection. Note the lowering, in fact, of the upper eyelids when looking down. 10 years after, when complaining about the gaze of the eye cube not being properly decoded by human partners, I remember we spent with Frederic weeks experimenting with a laser pointer adjusted to the inner eyes to check if there is a physical point of interest was right. We rediscovered the importance of conforming the eye morphology, the human eye morphology, and the eyelid eye direction coupling for optimal gaze direction decoding. And we end up with this eye design features in C. Okay, after having tried, in fact, several of different iris dimensions and coupling and so on. So premise one, readability of movements, whatever good they are generated, may be degraded by improper design of segments realizing them. A second detail I want to discuss concerns multimodal orchestration. Most dialogue systems coordinate co-verbal gestures, gaze, deictic, iconic, or beat gestures with speech by enriching output text with markers that timestamp onsets of these co-verbal gestures with their reference, either lexical items or syntactic boundaries. When looking on the put that there task with Nina, we realized that such a rendezvous between multimodal events are not necessarily paced by speech. We may delay, in fact, speech output, waiting for endogenous gestures being performed, such as a deictic gesture when triggered lately, as well as exogenous gestures performed by our partners, such as waiting for overt acknowledgement by the addressee of any piece of information using, for example, gaze contact. The figure here shows that such waiting time is shared between final syllable lengthening, silence, and field pause, up to 3 seconds here, before the next part of the utterance is spelled. Incremental speech processing, generation, speech processing in particular, is one of the possible answers to this issue, as proposed by Sconcer and colleagues. So premise 2, robots are multimodal in, multimodal out machines with varying dominant modalities, and speech is not always the dominant modalities. The third issue concerns the collections of ground truth interactive data for feeding state-of-the-art statistical models. Even transformers are programmed with data. Training human-to-robot models, HRR models, with human-to-human interaction exemplars may be misleading because, one, expectations and therefore behaviors of human partners differ when facing a congener versus a robot. Second, the cognitive and sensory motor abilities of a human tutor cannot be entirely mimicked by the robot. This mismatch between training and inference may be improved by reinforcement learning, but this process is slow and requires the estimation of suitable reward. These points could be partially resolved without those experiments, but immersive operation nicely complements the cognitive gift of the pilot with sensory motor handout, given suitable embodiment. At GypsaLab, we developed such an immersive platform for Nina. The sensory motor embodiment of the pilot, here, into the robot is fulfilled by forwarding his binocular and binaural signal to the eyes and ears of the pilot, and mapping back the eye, face, and head movements of the pilot to the corresponding segments of the robot. We especially worked on gaze control, in particular on eye divergence. That is important, so important, for the active perception of depth for the pilot and the distance of a point of interest of the robot from the user's perspective. Let's illustrate this platform with a video.
Head, literally. From a control center next door, an operator wearing a connected headset can teach her in real time how to behave during a conversation. This immersive visual experience is made possible thanks to the cameras installed in Nina's eyes and the microphones in her ears.
Bonjour.
Hello, I'm Nina, the humanoid robot of the GypsaLab, and I'm currently being operated by Gérard Bailly.
The robot then replicates the movements of the operator's head. His eyes are tracked by his headset and mirrored by the cameras in Nina's eyes.
Premise 3, in fact, data collection matters, in particular, when this is the main way to program behavioral models. The very first minutes of social interaction are crucial for humans, as demonstrated by the work of Alex Pentland on speed dating. Our multimodal behaviors trigger cognitive expectation from our partners that strongly bias subsequent interactions. This initial social bonding impacts cognitive activities of our partners, even when they are not involved in shared tasks. We recently collaborated with sociologists and psychologists of Clermont-Auvergne University on the impact of social presence of robots on humans, more specifically on executive functions as involved in decision-making. In this study, subjects perform a Stroop task. For those who doesn't know, it's deciding about colors of words or symbols displayed on screen with conflicting content, as an example of the words blue or sea written in red. In presence of Nina working on its own at 2.6 meters. After being introduced to it, during this short anthropomorphization period, lasting less than 5 minutes, the robot was introduced by the experimenter and showed on what it was working. It was working on evaluating sessions of Stroop versus flanker, determining the direction of an arrow, also in conflicting context, supposedly performed by previous participants. Then the subjects move and perform their Stroop task. We showed that mean response time of that test is significantly increased when Nina competence on Stroop was induced, but not when it was competent on flanker. Note that both conditions imply judgment skills from Nina. So the way robots present themselves impacts their representation in humans' mind. Premise 4, first contact should be parameterized with caution. The last issue I want to raise concerns evaluation. Usual evaluation procedures are performed offline using questionnaires or recalls. Such global judgments are partly conditioned by key episodes, the impact of which are often difficult to sort out. It is interesting to identify inappropriate behaviors, if any, for resolving their causes. Using replay of simulated interaction between Nina and an elderly person during neuropsychological interviews, we showed that the density of yuck response, so people were pressing the bar key, the space bar key, each time they thought that something was going wrong. This yuck response collected online spot such interaction bolts. The blue plots, here it's time, here it's the number of yuck response, so this density of plots of number of time the spacebar was pressed. The blue plot displays the York density of the first version of our behavioral model, computed with responses of 53 viewers. You have extrema. These 26 extrema have a clear interpretation in terms of speech, gaze, hand gesture, improper behaviors. Once the inappropriate behaviors were corrected, the interaction was replayed and judged again by 46 viewers. And this density is plotted in rows. The correction results in an effective improvement. The peaks are lower. That generates new expectations, in particular, the lack of emotion feedback featured in yellow and cyan here, which were not, in fact, yucked in the previous one. Premise 5, global judgments are biased by episodes of interaction. It's interesting to look at these small episodes. I tried here to sketch out elements of a research program that balances between the enrichment of the sensory motor, cognitive, emotional, and social skills of a robot, and the thoughtful evaluation of these components by human partners. So one way to improve the readability of robots' mind could be to use these robots to probe human cognition, mirroring the use of humans to enrich artificial cognition. Let's use robots to probe human one. In order to social robots, in fact, to become social congeners, we need to understand, model, and test co-adaptation mechanisms in a more balanced way. These ideas and works are high-hanging fruits, picked during several projects and together with collaborators. Nothing would be possible without their support. Surely, I've been going through these points too rapidly. If you understood, it's certainly because I did not explain the right way. So now I'm ready for questions or suggestions.